Just like exponential growth, we can also look at exponential decay. You could actually model it with the exact same formula, it's just the coefficient will come out to be negative in that case. In the notes here, I present it with a negative exponent already embedded in the formula. So we'd have a positive r, but then a negative value when we plug it into the formula. And you could call it anything you want. Here we're calling it m for mass, because decay models and lots of things decay over time, but a very common example is radioactive decay, where a radioactive substance will decay over time. And when you have something that decays, there's going to come a point to where it's half the quantity it started at. And then, of course, over time, it keeps cutting in half and in half and half. That time is actually constant, the amount of time it takes to cut in half, so they call that the half-life. And you could actually solve the equation and come up with a formula for r based on the half-life if you wanted to. I usually just plug the numbers in and work it out each time, but there is a little formula of how r and the half-life relate to one another. But to find that, you just use m sub 0 and 2 times, or 1/2 times m sub 0, and solve the equation. So let's look at an example of a radioactive substance. Polonium-210 has a half-life of 140 days. Suppose that a sample of this substance has a mass of 350 milligrams. Part A, find the function that models the amount of the sample remaining after time t. Part B, find the mass remaining after 1 year, and here be careful with the units. Your t value is going to be in days if we use the half-life of 140 days, so 1 year will be at 365 days. How long will it take for the sample to decay to a mass of 275 milligrams? That'll require us to solve an exponential equation, and then we'll look at a picture of the graph. Let's see, popped up in the wrong order there, but let's read through the solution that I have here. So you can use the half-life formula if you want to. I always prefer to solve the equation so I don't have to memorize formulas. It's a little more work here, but it's the type of work I have to do on other parts of these problems anyway. So we have an initial amount given in the problem of 350, so we plug that in. And we've got e to the negative RT. And we don't know r, that's, again, we can find it using the half-life, or we can plug in. We know that if we plug in 140 days, so plug in 140 for t, you'll get half of the 350. Okay, so you get 175. So there's our formula plugging in the half-life. We have our initial value of 350 times e to the negative 140r equals 175. Divide both sides by 350. You're doing a half-life problem. You get 1/2 over there. And you take the natural log of each side. You get natural log of 1/2 equals natural log of that. Wipes out e. Divide, you got r's natural log of 1/2 divided by negative 140, which comes out to be positive because the natural log of 1/2 is negative 0.00495. Okay. That looks a little bit different than the half-life formula I had on the other slide. You can rewrite that as 2 to the negative 1 and bring the power out and write it with a natural log of 2, but it's also the natural log of 1/2 over negative whatever the half-life is. But we wind up, when we plug back into the formula, again, this power will be negative. We have negative RT in our formula here. So we have 350 e to the negative 0.00495 t. Okay? You always want to use at least 2 or 3 non-zero digits. Part B, for a year, we can plug in 365 days and evaluate it. So we just punch that number in our calculator, 350 times e to the negative 0.00495 times 365, you get 57.5 milligrams. Okay, part C, the equation we're going to have to solve here. So back in part A, we found our full formula, we found the r value. Now we're going to figure out what t value will give us 275. And the work here is, aside from solving for t instead of r, it's identical to what we did on part A. We're solving this exponential equation. You divide by 350. It's not half-life now, so you don't get a half. We're going to get natural log of whatever 275 divided by 350 is. Natural log of the other side wipes out e. You just get the power. Divide by the negative 0.00495, and you get your answer, 48.7. Okay? So sometime between 48 and 49 days, if you round to 49 days. And then the graph, put your formula in, use x instead of t. Again, you may have to play around a little bit, but figure out an appropriate window. And again, this is not a perfect window. It's just you have to find a window that shows you the graph. And there you go, exponential decay. Okay, here's a formula that has an exponential decay piece involved in it. This is Newton's law of cooling, which is a very interesting function that Newton came up with. So if D sub 0 is the initial temperature difference between an object and its surroundings have temperature T sub s, then the temperature of the object at time t is modeled by this function. So we can determine the temperature over time of an object. It calls it the law of cooling because the object's going to cool off over time in a regular environment unless you put it in an oven or something. So here's a cup of coffee left sitting in a room. Okay, it starts at 200 degrees Fahrenheit and it's going to start cooling toward room temperature. So a cup of coffee has a temperature of 200 degrees Fahrenheit, is placed in a room that has a temperature of 72 degrees Fahrenheit. After 10 minutes, the temperature of the coffee is 160 degrees Fahrenheit, so you could measure that. And we can use Newton's law to come up with a model here for part A. We're going to find a function that models the temperature of the coffee at time t. And then after that, we'll figure out what's the temperature at 15 minutes, how long will it take it to cool to 120 degrees, and draw a graph. Okay. So let's tackle parts A and B. So part A, we had the formula given to us. We need T sub s is the temperature of the surroundings. D sub 0 is the difference between the 200 degree coffee and its surroundings, the 72. So we subtract and get 128. You plug those into the formula that we had for Newton's law of cooling. We have 72 plus the difference, 128 e to the negative kt. And to find k, we have to plug in another point. Well, we know if we plug in 10, we get 160. So t of 10 will be 160, and then by the formula, it's 72 plus 128 e to the negative k times 10. So we subtract the 72 from 160, we get 88, then divide by 128, then take the natural log of both sides, which just leaves you with negative 10k on the side that had e. And then you divide by negative 10 and you have your answer. The natural log of 88 over 128, that quantity divided by negative 10 is 0.0375. So we have our function, 72 plus 128e to the negative 0.0375t. Okay. And then on part B, you just plug 15 into that. You can evaluate that expression with your calculator. I got 145 degrees. So it starts at 200. After 10 minutes, it's 160 degrees. And now we know after 15 minutes, it's 145 degrees. Part C, when will it be 120 degrees? Well, you can solve the equation. You plug in the 120 for the output and solve for t. Again, very similar to how we found k. Subtract 72 from both sides, divide by 128, take natural log, which will wipe out the e. So we have natural log of 48 over 128 equals negative 0.0375t. Divide by the coefficient, negative 0.0375. Get our answer, 26 minutes. And then the graph, we get an interesting graph here, 2 plus 72. Sorry, the cursor was on the screen when I did the screen capture. 72 plus 128e to the negative 0.0375x. Again, work with it a little bit till you figure out a good window. And there's the graph. This one has a horizontal asymptote. You can think of it, you have an exponential function with a horizontal shift. You have the plus 72, so it has a horizontal asymptote at 72, which makes perfect sense if you think about it. You have a 200 degree cup of coffee, it's going to cool off until it gets to room temperature. It won't go below 72 degrees because the room is 72 degrees. Okay, and then we're going to end with just going to go kind of quickly through some extra applications of logarithms that you see. So where do you use logarithms? Well, in chemistry they use logarithms. Anytime you have quantities that are really, really large or really, really small or that differ from each other by really large amounts, they use logarithms. So in chemistry, the hydrogen concentrations, they're really, really small numbers in scientific notation. So chemists measure the acidity of a solution with what they call the pH value, which is negative log of the hydrogen ion concentration. And there's their notation, the brackets, H to the plus for the positive charge. And that's the common log, log, log base 10. Okay? So this helps them avoid very small numbers and negative exponents. And they've defined the pH of 7 to be neutral, like purified water would be a pH of 7, it's neutral. Below 7 is acidic, above 7 is basic, or a base. So let's do an example in each direction. The hydrogen ion concentration of human blood was measured to be 3.16 times 10 to the negative 8 moles. Find the pH and classify the blood as an acid or base. So you just plug the number in and compute it, negative log. It's close to the exponent, but it's a little, you have the 3.16 that changes the number a little bit, but and the negatives cancel. You get 7.5. 3.16 times 10 to the negative 8, do the logarithm of that, and then do negative that, you get 7.5. So it's slightly basic, just over 7. The most acidic rainfall ever measured occurred in Scotland in 1974. Its pH was 2.4. Find the hydrogen ion concentration. There you have to solve the equation, and I've changed the hydrogen ion concentration symbol to an X to make it easier to compute here. So we know the pH is 2.4, and the pH is negative log of the hydrogen ion concentration, so we solve for X. Get rid of the negative, multiply both sides by negative 1, and then rewrite it as an exponential, or do 10 to both sides. 10 to the log of X gives you X, equals 10 to the negative 2.4, and you evaluate that out, it's 0.00398. I don't have any problems that I'll work out here, but just to show you some other examples of where they use logarithms. Earthquakes measured with the Richter scale, those are logarithms because the difference between, say, a 4.0 and a 5.0 or a 5.0 and a 6.0 is actually a magnitude of 10. It's a very large difference. So they measure these things with these logs of these ratios. So your Richter scale measure, M, is equal to the common log of I over S, where I is the intensity of the earthquake you're measuring, and S is what scientists have measured as the standard earthquake. 1 micron, 10 to the negative 4 centimeters. Decibel level is actually very similar to the Richter scale. You have a log with a ratio inside. The decibel level that you use to measure the intensity of a sound, how loud a sound is equal to 10 times the common log of I, the intensity of that sound, divided by I sub 0, which is they say the threshold of human hearing, kind of the standard level for a sound. And that's it for the 4.5 notes. Thank you.